Hello, Algebra 1. Here we are again, still in Chapter 1, but coming to the end. We will discuss today the concept of functions. Here is a quick look at the words, at the vocabulary that we'll have, and the different types of functions we'll talk about. So we'll talk about what a function is, discrete function, continuous function, the vertical line test, which is used to determine if you have a function, and nonlinear functions. So a function is a relation in which each element of the domain is mapped to or paired with exactly one member of the range. And sometimes we need a visual to think about this, so let's take a look at a relation. Okay, I have two relations here, one in black and one in pink, that represent two situations. And I know they happen to each have 4 elements, but they could have more. So with this first one, we've got 2, 4, 6, 8, 11, 9, and 8, 7. 2, 6, 11, and 8 are elements of the domain, and notice that they are mapped to exactly one element in the range. They're mapped to a unique value. Let's look at this next pink example. 2, 1, 4, negative 1, 2, 7, 3, 2 are elements or ordered pairs in this relation, and we see we have a problem. 2 is mapped to 1, and 2 is mapped to 7. That's a no-no. This is not a function. This guy is a function. Now that we know what a function is, we can talk about different types of functions. A discrete function and a continuous function are best identified by their graphs. So if you had a function like this where all of the elements of the function were separate dots, or separate points, then that would be discrete. It's not continuous, it's not connected. And a continuous function would be a function that you're probably pretty used to seeing when we graph a line or something like that. That's considered a function. You could also have a continuous function if you had, and I don't know if you guys remember this term, but if you had a picture that is a parabola. Do we remember what a parabola looks like? Kind of a U-shaped figure. That is also considered a function. Well, not just considered a function, considered a continuous function. Okay. The vertical line test is a test that you can use to determine whether you have a function or not when you have a graphed relation. And a nonlinear function is really a straightforward one. This is just one where we think about if you don't get a line when you graph it, then it's a nonlinear function. So the examples that I had, or the example of a parabola is a nonlinear function. The example of some kind of a little swervy line like that would also be a nonlinear function because it doesn't form a line. Vertical line test, let's talk about that for a moment. If I have a graph or a relation that I can graph and it looks something like this, and this does happen, would this be a function? Would this represent a function? Some of you are screaming, no. Some of you are screaming, I have no idea. Some of you are screaming, just get on with it. So let's get on with it. The vertical line test tells you that if you have a graph of some function, or some relation rather, and you draw vertical lines straight down, if any of those lines hits more than one point, you know you don't have a function. And let's think about why. So here, according to the vertical line test, we don't have a function. So let's figure out why that might be. In this case, I could say that this is like 4 on the x-axis, and I could say like this is maybe 2, and this might be 5 or something like that. So if that's the case, this point would be labeled 4, 2, and then this point over here would be labeled 4, 5. And I think hopefully you guys already see it. When the line hits 2 points, when a vertical line hits 2 points on a graph, we know we don't have a function because one element of the domain is mapped to 2 different elements in the range. That brings us to our first example. Example 1, identify a function. So we're going to determine whether each relation is a function. So we remember relations can be written in several different ways. Here's this first example, A. That's a mapping. So as we look at this mapping from -2 to -3, 0 to 6, 0 to 6, 3 to 6, and 4 to 9, would you say that this is a function? Hopefully the answer is yes. Even though 0 and 3 both go to 6, notice that 0 only goes to one number and 3 only goes to one number, even though they happen to be the same number. So yes, this is a function. Indeed, it is a function. Let's look at this next guy over here. So we see that 1 goes to 4, 3 goes to 2, 5 goes to 4, and 1 goes to -4. Is this a function? I know that's kind of hard to see, but is this a function? Can you tell? I hope you realize that it's not, and it's not because of these 4s. Those 4s are not a problem at all. The problem is the 1. With 1 being mapped to 4, or associated with 4, and then 1 being mapped to -4, that is the problem. So that would not be a function. Not a function. There we go. Example 2, we're going to draw graphs. So the above table represents 5 teams in an ice sculpting competition and the heights of their sculptures. Okay, so the first thing we need to do is to determine the domain and range. And from the last section that we talked about, hope you guys recognize that this is the domain and the range would be this set here. So I'm going to write those in set form. So these two sets are the answer to part A. We've determined the domain and we've determined the range, and we wrote it out in set notation. The second part, part B, it says write the data as a set of ordered pairs. Hopefully this is pretty straightforward too. I think you guys see this is pretty straightforward. There are all the ordered pairs, and then so what we're going to do is take these guys and we're actually going to graph them. And I don't have this space, so I'm going to delete these, and then I'm going to put the graph here for us. So when graphed, we should get something that looks kind of like this, and then finally we'll answer C. It says, state whether the function is discrete or continuous, and explain. The answer is obviously that it's discrete. It would make no sense to connect the dots here, because in connecting the dots, we're saying that there's some other values in between, and there's no team like 1.5 or 2.5, and there's just no other data that makes sense there. So we will not connect the dots. Doesn't make sense to do so, but we will say that it is a discrete function. Example 3, we're looking at equations as functions. We're going to determine whether this particular equation represents a function. So in order to make this determination, we're going to graph the function, and then we're going to set up a table, get some values, graph the function, and then do the vertical line test. So I just chose at random -1, 0, 1, and 2. When I plug them into the equation for x, I get the following. So I get those corresponding values, and now what I'm going to do is plot the point. So I need to label my axis accordingly. The x-axis is no problem, just 1 and 2 would be fine here, and then rock a little -1 back here. But the y-axis is a little bit difficult. We need to go up to 14, and we need to make sure that we number things in a more in a reasonable way. So watch. I was able to write down or to space out 9 spaces pretty evenly. Since I want to get all the way up to 14 and 9 doesn't get to 14, I'm just going to count by 2s. Now that I have my labeling done, I'm going to plot the point. So at -1, we're at +5. That's right here. At 0, we're at 8. At 1, we're at 11. And at 2, we're at 14. So we have this gorgeous set of points that lay beautifully in a line. And we can see that if we were to continue to go on and on, for each value in between, we would get this line. So now we're going to do our vertical line test. And if you notice, when I draw vertical lines straight down, it's all good. None of these lines will ever hit twice. So I know that indeed this is a function. Let's go on to example 4. Example 4 introduces the notion or the notation of functions. And so function notation, as you see written here, this would be read as f of x, yes, f of x is equal to -4x plus 7. And if you've seen this before, you know that we say that, well, f of x is just another way of writing y. Somebody right now is saying, why do we have to write y differently? Why do we have to write it differently? It gets to be really helpful because when you see things like f of 2, that means what is y when x is 2? Right? That's a whole lot to write. It's easier just to say, hey, f of 2, what is f of 2? And we'll talk about how to calculate that. So to answer this first part A, I like to actually rewrite f of blank is equal to 4 times blank plus 7. What I've done is I've left a blank everywhere x is because f of 2 tells me to replace x with a 2. So I'm going to now put f of 2 here, and what I do is I replace, I forgot the negative, sorry about that. I replace x with the 2. So now I've got negative 4 times 2 gives me a negative 8 plus 7. Negative 8 plus 7 is a negative 1, and there's my answer. F of 2 is equal to negative 1. Let's try the next problem. So here we have again rewritten f of blank is equal to negative 4 times blank plus 7. We're going to place negative 3 in. So f of negative 3 is equal to negative 4 times negative 3 plus 7. And then I'm going to do exactly what sorry that 7 looks terrible. I'm going to do exactly what I did last time. Negative 4 times negative 3 is a positive 12 plus 7. 12 and 7 gives me 19. And that's the answer. F of negative 3 is equal to 19. Finally, we have our last example, example 5, the nonlinear equation. Now, when I do this on PowerPoint, so these big old 2's should be exponents. So this should read h of t is equal to negative 16t squared plus 68t plus 2. And what we'll do is we will, as you probably guessed, to calculate h of 4, we're going to have to substitute in 4 for all the t values. The substitution looks like this, and then we'll use PEMDAS to calculate, or order of operations to calculate our answer. So we get this, and then 18 is our final answer. So that all of that was for part A. And now let's look at part B separately. Let's remember what we're starting off with in terms of the original equation, and now let's think about what they're asking here. So it says 2 times h of g. We know what h of t is. H of g would simply be to replace g everywhere we see t. So I'm going to write, oh, t's not there, sorry about that. So I'm going to write g instead of t. After replacing g, we are asked to multiply this whole thing by 2. So if I'm going to do 2 times h of g, I've got to multiply h of g times 2. And my result comes with a little bit of distributive property. When I distribute 2 throughout the whole expression, I end up with this. Negative 32g squared plus 136g plus 4. Our assignment is as follows. We've got pages 50 to 52. Please complete all of the problems here, and I'll see you guys tomorrow.